Good morning, everyone, and welcome to those of you who just joined us. This will be our second presentation of the 2021 Capstone projects. Just to reiterate what I mentioned before, the presentations will go for about 20 minutes. Then afterwards, we'll have about 10 to 15 minutes for questions. I will be moderating those questions. So once the presentation is done, if you would just raise your hand on the bottom bar of the Google Meet, that little icon there, and then I will select the individuals who will ask those questions at the end of the presentation. The next presentation is going to be given by Brooke Schmelz, and it's on the evolving states of aerodynamics and sustainability. Brooke, take it away. You can start by presenting and sharing your screen.
Okay, can everyone see that now?
Yes, we can.
Okay, awesome. So hello everyone. Today I will be presenting on sustainability in aerospace, and you might be confused as to how these two topics relate. And I was in the same situation last year when I was trying to think of a capstone project. I wanted my project to include engineering and specifically the way that math can be translated into real life problems. But I wanted to connect these ideas to the climate crisis and sustainability, which are currently very prominent and popular topics. So my goal by the end of this presentation is to give you a better understanding of how engineers are currently working on creating more sustainable airplanes. So as I said before, you might be confused about how sustainability and aerospace can work together. After all, an aircraft can burn up to a gallon of gasoline a second. And as of right now, engineers have not created a large-scale zero-emission aircraft. But there is evidence that one could be coming soon. And from my research, I have found that the process of creating sustainable airplanes can be split into two phases. The first phase, which is the one currently making the most impact, is the optimization of current designs. And a big component of this phase has been the introduction of computer-aided design and computational fluid dynamics, both of which we will discuss a little bit later. But the next phase is the development of new technologies and designs. In order to create that zero-emission aircraft, there are still many technologies that must be fully developed before the new designs can be feasible. I will discuss these technologies as well as some of the designs and programs working to develop them a little bit later. But right now that we have an overview of this process, let's dive into the specifics of how engineers are actually working towards it. So the purpose of optimization in general is to take a product and make it better. And in aerospace, this involves taking a current design and making slight modifications. But these designs in the end wind up being extremely similar. And in order to understand which modifications engineers are actually making, we have to first understand some basic aerodynamics. So in this photo, you can see all the forces that act on an aircraft while it is in flight. As you can see, the lift force pushes the aircraft up, the weight force pulls it down, thrust propels it forward, and drag is pulling it back. So as soon as an aircraft starts moving through the air, all these forces are simultaneously created. And part of my research was looking into why this happens, but unfortunately this presentation is not long enough for me to discuss all those nuances. So you might have noticed that each force has an opposite. For lift, there's weight. For thrust, there's drag. And these are called the force pairs. They work against each other. So the more weight an aircraft has, the less overall lift effect. And the more drag, the less overall thrust. But a change in one force pair can actually have a large effect on the other force pair. And this has major implications on optimization. So let's take an example of force pairs in action. Say an engineer decided to put a larger engine on their aircraft so that they could create more thrust and therefore overcome more of the drag. So by doing this, they will overcome more of the drag on the aircraft. But that larger engine will also be adding a lot of weight to the aircraft and therefore canceling out a lot of the lift. So this is really important for engineers to keep in mind when they are making new designs and modifications. Every change they make has a direct effect on the aircraft, but there are also inadvertent effects, such as the one I just used as an example. And when it comes to sustainability, the force pairs are especially important because the main force we are focused on for its environmental impact is thrust, which is the engines and their burning of gas. So to reduce the environmental impact of the airplanes without changing the engines necessary to keep an aircraft in flight, because obviously you must have some thrust to keep an airplane in the sky, we would like to reduce the drag instead, because by reducing the drag, you need less overall thrust to fly the aircraft. And lift maximization and weight reduction can also benefit this cause, but again, in this presentation, I don't have enough time to go into all the little nuances of that. So now that we have a general idea of the forces, let's take a closer look at the lift force. As I said before, it is an upward force on the aircraft, and usually when we talk about lift, it is in relation to the aircraft wing, as shown in this picture. Other components of the aircraft can create some lift, but the wing has the biggest overall effect. So when an aircraft begins to move through the air molecules begin to flow over the wing. As these particles move over the wing, an interesting phenomenon happens where the air on top of the wing moves at a higher velocity than the air below. And this creates a low pressure area on top of the wing and a high pressure area below it. This difference in pressure is what causes the lift force. Now, it's important to mention that this can only occur if the air molecules stay really tight to the shape of the wing, or attached to it, as we like to call it. Should these air molecules detach, such as just move straight back and not follow the curvature of the wing, then no lift would be created and the wing would be stalled out. And this has a lot to do with the shape of the wing. Engineers have experimented with plenty of different designs, but the tried and true version that we see on most aircrafts today is the one shown in this picture, which has a relatively flat bottom and then a more bulbous top. So now that we understand lift better, we can talk about drag, and which I said is one of the most important forces to talk about when we want to optimize our aircraft, and especially for sustainability. Now, there are many types of drag, but for the sake of time, we're only going to discuss one specific type that is actually created due to the effects of the lift force. Now, as we talked about before, the air molecules are moving around the wing, and on top there is a higher velocity, and on the bottom there's a slower speed that the air molecules are moving. And so when they meet up, these two different speeds meet up at the back of the wing, this causes something called the trailing tip vortex. And this is caused because, like I just said, this higher speed molecules are meeting up with these lower speed molecules, and they wind up spinning out and causing disturbances in the air. So even though this is at the back of the wing, it's still a major component of drag and has a major effect on the aircraft. So one of the biggest effects this has is the creation of this downwash that you see in the picture. As you can see, these downward arrows are representing that downwash. And this is an additional downward force that puts stress on the aircraft. And engineers are constantly looking for ways to reduce this effect. So one simple solution they have come up with is these winglets. And as you can see, it's just like a little upward tick on the end of the aircraft's wing. And you can see in this photo that it greatly reduces the effects of the trailing tip vortex. And this is because, like I said before, the air is traveling along this wing. But with the winglets, it is able to more directly flow from the front of the wing to the back, and this reduces that vortex which is created by the spiraling of the air. So this allows it to only occur at the very tip of it, and it makes it greatly reduces the effect of this. So now we've talked about lift and drag, we can really understand the effects of CAD and CFD. And these are some of my favorite topics I got to research in my paper, Computer-Aided Design, or CAD, and Computational Fluid Dynamics, or CFD. And one of the most important aspects of these programs is actually how they work together. Making these programs more compatible is one of their selling points. In CAD, it comes down to something called grid generation. Grid generation is done after an aircraft has been designed fully using CAD software, and the design is then carefully outlined with these grids. The process is essentially copying the design so that it can be transferred into a CFD program. Now, these grids are really more like equations that are trying to fit the outline of the aircraft as best they can. But they often have errors at sharp points or areas where the two parts connect. For example, where the wings meet the body of the plane and the sharp nose of the plane as well. The more accurate a grid generation program, the more accurate the CFD program will be able to be. But even once the grid has been completely generated and the design has been put into CFD, CFD has its own problems with equations. In general, the greatest enemy to advances in CFD are computational power. Current computers simply cannot handle the types of equations necessary to solve aerodynamic problems with extreme accuracy. Just to show you how complicated these equations are, this photo includes the Navier-Stokes equations, which are typically used to solve aerodynamic problems. In order to solve these problems at all, engineers have to leave some of the variables constant. But the more variables we can have while still receiving accurate results in a reasonable amount of time, the better it would be. So engineers are constantly looking for new equations that can get as close to matching the Navier-Stokes equation while remaining simple enough to solve. One example of such an equation is the B-spline curves. Now, this curve is extremely accurate and still only needs a few points of data, which makes it perfect for computing. But if you are having understanding what all this means, let's simplify the terms a little bit. So this is a random graph that I found online, and for the sake of this example, we're going to pretend that this graph represents the Navier-Stokes equations, and each point is a different aerodynamic property, such as lift or drag. Now, if we decide to use a very simple equation, such as this line, we are able to solve for two of the points. Perhaps these points represent pressure and time, two elements in the Navier-Stokes equations. Now, this will be very helpful for mapping out certain aerodynamic properties, but obviously we have not hit every point. So what if we use a more complex equation? This green line is still not a perfect match, but it gets a lot closer than the red line did. In the terms I discussed before, the perfect solution would be the full solution to the Navier-Stokes equation. So if we perfectly match the graph. The B-spline curves, which are still pretty complex, would be represented by the green line. They get a lot of the answers, but are still not perfect. And the red line would just be previous very simple equations that don't solve for as much as we would like. So now let's get back to how this all relates to sustainability. The more accurate these programs become and the more precise engineers can become with their designs, the better it will be for sustainability and optimization in general. Already, CAD and CFD have provided a lot of freedom for engineers to experiment with really unorthodox designs. Before the introduction of these programs, the only way for an engineer to test their design was to make a physical model and go through extensive wind tunnel testing. all of which is very expensive, time-consuming, and the designs were not even guaranteed to be viable. So of course, companies were hesitant to spend so much money on such great risks. But with CAD, it is very cheap and easy to test out new designs, which has led to many advancements in the industry, including more unorthodox approaches to the sustainability problem. And we'll see some examples of these designs that I'm talking about next in future technologies. So first, before we get to the designs, we are going to talk about alternative fuels, which, since pollution is caused by the burning of gas, it makes sense to replace it with something else. And one solution is using some type of battery. But obviously, to fly an aircraft, these batteries need to be extremely powerful. And one technology engineers have been working on is called Lithium Air Batteries. These batteries are extremely light, but have an energy density close to that of actual gasoline. This means that for a certain volume of the batteries, they are able to hold the same amount of charge. The only difference is the batteries are way lighter and they are rechargeable. So it would seem obvious that engineers would like to use this technology as soon as possible, but it is not perfect, and there are some issues that engineers have run into. The main one being the fact that the electrolyte solution in the batteries that holds their charge degrades every time the battery is charged. And this means that every time it is charged, the max amount of energy the battery can hold decreases. Now, should engineers find a electrolyte solution that does not degrade, this could immediately lead to huge advancements in sustainability across many fields, not only aerospace, but many other fields as well. Now, the other major project in aerospace is working towards hydrogen-powered flight. This is being studied currently by NASA in their cryogenic high-efficiency electrical technologies for aircraft program, and to shorten that very long name, it is known as CHEETAH. So hydrogen flight uses cryogenically frozen hydrogen, and the combustion is set off by the air around the engine. These engines are actually way more powerful than a typical engine. And this is due to the fact that more of the power created is used directly for thrust rather than burned off as heat. But the main problem with this system is integrating it into current designs. There would have to be a completely new design to carry these components, which we will talk about next in the ZEST design, or the Zero Emission Hypersonic Transport. Now, this is currently being researched by the Japanese National Space Agency, or JAXA. The key to this design is the ramjet engines, which utilize the cryogenic hydrogen fuel we talked about earlier, but this design uses cryogenic oxygen to ignite the hydrogen. And again, the problem they are having is integrating hydrogen in a compact way, since, as you can see, it takes up quite a bit of space and leaves very little room for cargo and passengers. So now that we have discussed one new design that has been created for sustainability, I'd like to bring up another one that I like to refer to as the holy grail of the aerospace industry. And this is the Progress Eagle design. And before I start talking about the design itself, I just want to point out that pre-COVID, it was estimated that all the technologies I will be talking about for this design could be available as soon as 2030. And now let's get into the features so you see how impressive that number is. So the aircraft has 3 stories, can carry 800 passengers, uses those hydrogen engines we talked about previously, solar panels on the roof and the wings so it can power itself, and even a wind turbine on the back. And this aircraft also uses some technologies that have not been created yet, which are the quantum solar cells, nanowires to kinetic power, and microwave radio wave harvesters. Now, all of these are fairly complicated individually, but essentially they are all used to transfer power between the different components of the aircraft. So we saw the solar panels and the wind turbine. All of these would essentially be used to transfer power back into the aircraft. And should they actually be developed soon, this design could become a reality. So let's look at this design. So this is one photo of it. And it's a little hard to tell here, obviously, because it's not compared to anything else, but this design is massive. And you might also see that the winglets we talked about earlier are utilized in this design. And here's a more close-up look. And you can see this is bigger than the winglets we were looking at, which were just a simple upward tick, but this one is much larger. And this is actually a photo of them folded in, because in flight, they fold out to be properly utilized. And in this photo, you can see that they actually have 3 different ones on the end of the wing. And this is because these wings are so much larger than any other aircraft wing that they are creating a lot more drag and they have a lot more forces acting on them. So there would have to be more to reduce the effect of that trailing tip vortex, which on a plane this large would have a massive effect. You can also see here that there is a little cabin right on top of where like the pilot would sit, and this would replace first class, and apparently it would have like 180 degrees views, so it would be, you can get a little bit of a better view of it here. So that last design was all I'm going to talk about today, but before I finish the presentation, as for questions, I just want to say a huge thank you to Dr. Delgado and Mrs. Hodson, who have been so helpful through this entire process and really made this a really enjoyable process for me, as well as like family and friends who all supported me through all of this. But yeah, that's all I have to say for now. So if we want to go to the questions.
All right, Brooke, that was a wonderful presentation. Thank you very much. If we could stop presenting right now so we can see the audience, and we will identify if anyone has any questions. As a reminder, just go to the bottom bar of the Google Meet and just hit the upward hand, and I'll be happy to pick on you or select you, choose you. Jaron, looks like you have a question. Go ahead.
I do have a question. Hi, Brooke. Good job. What made you decide to like specifically do a project on the aerospace industry as opposed to like anything else?
Yeah, thanks for the question, Jaron. As I said in the beginning, I did want to do this project on engineering, but what made me decide specifically on aerospace was actually a project I did in robotics last year, where I built my own remote control aircraft. And originally that was going to be part of my project where I would design and build my own aircraft. But with time constraints and everything that went on with COVID, that didn't wind up being a good use of my time. So I decided to work more on the research. But I was really interested in the way that math related to the aerospace industry. And I just thought of all those forces I talked about, I find them really fascinating.
Great. All right, let's see. Next question, Claire.
Hi, Brooke. Great job. Do you plan on continuing to study aerospace engineering in college?
Hi, Claire. Thank you. That's a good question, too. Yeah, I actually do plan on studying it right now. Of course, things might change. But as I said, I'm really interested in the way that science and math all relate to putting a massive aircraft into the air. And also this relates to what happened just yesterday with the first flight on Mars, which I don't know if anyone saw that, but that was crazy that they were able to gather enough information to figure out the different aerodynamic properties on Mars and actually fly on Mars, which is just crazy to think about. But yeah, I would love to be part of projects like that. I think it's fascinating, and I would love to continue to study it.
Do we have any other questions from the audience? Well then, Brooke, I will jump in with my question. You actually mentioned 2 different things. One, COVID seems to have prevented some of the plans that you originally had for this project. And yet we have NASA doing fantastic things on Mars with all their scientific input and the ability to engineer in that atmosphere. So let's combine the 2. Do you really think it's feasible with COVID occurring right now that by 2030 we'll have this new hydrogen-powered airplane or sustainably powered airplane?
Thank you, Dr. Delgado. So I do think it's feasible. It might be a few years later than they originally thought, but a lot of companies have fully come back now and dedicated themselves again to these programs. Like I said, in COVID, a lot of them did cancel these programs in favor because the aerospace industry wasn't doing so great with no one was flying, obviously. But now they're kind of back in full force. And I just saw the other day that there were, I believe it was Airbus or Boeing, one of them, just released like 4 new zero emission designs that they are currently working on that could be ready by 2030 or a year around there. So I do think it is possible. I do think it'll happen. And I hope I get to be part of that.
Do we have any further questions from the audience? Claire, you have another one.
Yes. So I just was thinking, Brooke, when you were talking about how they're trying to make a hydrogen plane, and is there a goal in the aerospace industry to reach zero carbon emissions? And if so, do you know when that date would be?
So pre-COVID, it was around 2030 that they were hoping to have the first large-scale like commercial aircraft that would be zero emission. But now they're just like, I think they're still trying to hit that date, kind of. That's their hope, that they will still be able to get some zero emission aircraft out by 2030. But I don't think that they have really officially like said a new one. I think they're still sticking to that and just trying to work through it.
Right.
Yeah.
Would they be able to use that zero emission plane all the time, or would it be like kind of half and half, or do you not know? I'm just...
So that's a good question. I think they would be able to use it all the time. I think that's kind of the problem, is that they want to make sure, because with aircrafts, like it's kind of hard to go half and half. It's really like either it's going to be like you really want an aircraft to work all the time, right? So that's kind of the problem, is making sure that these aircrafts are safe to fly on a regular basis and figuring out maintenance for them as well. I recently saw a design where they were trying to think if releasing the cabin of an aircraft for when it crashes, so that you'd be separated from the engine, so that if there was an explosion with the engines, you'd be separated. But the main problem with utilizing that type of the design is safety and maintenance of the airplane. So I think that's a big component of this, is them figuring out how to maintain these aircrafts as well.
Yeah, that's a great answer. Thank you.
Do we have any other questions from the audience? Well, I'm going to put in an observation, and I'm jumping the gun a little bit because Emerald will be doing her presentation on Thursday on computing, and she'll be talking about quantum computing. She and Brooke need to get together and figure out the quantum physics to make sure this is all works. See, this is the future right here. We're going to have this done. Thank you again, Brooke, for a fantastic job. Claire, wonderful presentation. Thank you all for attending, and I just would like you to know and remind you that we will have videos of these presentations put online for you to be able to access. We're also going to try to get the final capstone presentations there so you can read really all the findings of what the students have put together. And as a reminder, tomorrow at 11:10 a.m. on this same Google Meet, we will have Devin Bhatnagar presenting his capstone presentation, and I hope to see you all there. Thank you very much. Thanks again, guys. Great job.
Thank you.
Yeah.
Thank you, Dr. Delgado.
Yeah, you guys did a great job. Bye-bye. I should just stay off campus tomorrow, right? Just do it at home.